the three general themes of this meeting. Well, I guess technically there are four: the sort of architecture, and then analysis, and then also visualization and decision support. I'm going to talk about analysis. So I have these sort of 5 steps that I think are instrumental to transforming care. I keep reusing them. Nobody else has adopted them yet, but I keep hoping Randall will use these instead of the other specific aims we have. These are better and clearer. But first and foremost, good. We need large stores of highly detailed granular data. Everybody recognizes that. We're all working on it. I want to reiterate what Jeff Hammerbacher said yesterday, that Andrew also reiterated, that lots of other people have echoed, that we have to start by getting data. That if we spend our time paralyzed by decisions about data models and how to store the data and all that, that we find that years will go by when we've collected nothing of any value. Whereas if we start writing it down, we have it, and you can start incrementally doing useful things with it. Robust, flexible data management. This always gets skipped over. The NLM pays lip service to it, but they don't value it as much as they say they do, I don't think. And I think we need to start making this a more important feature. Everyone wants to get on to the exciting stuff, analyzing the data, but this really needs to be emphasized and worked on. Techniques for turning big data into information. So that's what I'm talking about today, of course. Actually, that's my A story. I'll explain what I mean by that in a second. Effective delivery and display of that information. So Jeff talked about that, and you're going to hear a little bit more of it after me. And then the fifth thing is clinicians and researchers who can use these tools. So this came up during the analysis panel, this idea that doctors are idiots and don't know anything about math and they won't understand what we're doing, which I think is a little uncharitable, but also kind of true. I think computer science, machine learning, and things like that are moving at a really, really rapid pace. And something that was pointed out on the panel is that in fields where data became ubiquitous, machine learning has taken over. Computer vision, NLP, speech recognition, approaches to doing research there that don't use machine learning have basically fallen by the wayside. I think the main reason that that hasn't happened as much in medicine yet is just because the data hasn't been available. But once those things start penetrating, we're going to need a new generation of clinical researchers who know how to use them. People like Suchi are going to be sort of the hot commodity, people who understand the domain and start to really get a feel for the medicine, but also are experts on the machine learning itself. But we don't have very many Suchis yet, so we have to find another way. And that's going to be the B story of my talk today. I'm borrowing that lingo from my girlfriend Teresa, who is a screenwriter. You know, A stories and the B story is sort of the plot that's going on that's not really the really important part. But it is here, actually. So I want to go to the B story first, believe it or not. That is the value of multidisciplinary teams. I think this is something that's sort of been latent in the discussions here, but that we haven't really gotten into. Because Suchi Saryas are extremely rare, we have to build multidisciplinary teams. Clinicians, there's lots of clinicians here who are making great strides trying to apply machine learning to their data. But I think one thing that was made clear on the analysis panel that John pointed out is that they'll never be quite as good as machine learning people are at applying those methods. And that sometimes if you can just get the machine learning people the data, they're going to take it really, really far. Maybe there's a limit to what they can do if they don't understand the domain, but we certainly haven't approached it yet. We haven't even gotten them the medical data yet. And we heard this multiple times. I think Jeff Hammerbacher had his example about the adverse drug reactions that they discovered doing just some brute force data mining. That was interesting. Jonathan Gluck yesterday talked about the data competitions and the fact that there are people out there who make tons and tons of money analyzing the stock markets, and their idea of doing fun things is to go do these data competitions in their free time. And maybe if we threw up some medical data in front of them, they could discover some breakthroughs or maybe find some interesting new things in that data. Let me explain these two quotes that are sort of come from two sources of wisdom that I admire greatly. First, every person you meet has something to teach you. And then second, still it might be well for all if these strengths were joined and the powers of each were used in league. These come from my father, Robert Cale, and Glowin the Dwarf from The Fellowship of the Ring by J.R.R. Tolkien. The idea is we want to see more multidisciplinary teams, more interinstitutional collaborations. Stop doing your research in a closet. There's something to be said for that. You can be very productive if you put your head down and get some work done. But if you hoard your data and your methods and you don't share them and you don't work with other people, you're not going to be nearly as productive. John mentioned this, that we were talking about open source. We talked about open data a little bit. Also, open academia. We need to collaborate more, and especially across disciplines. And this is something that we've started doing, particularly since I arrived here. This is the team that is like growing every day that's working on CHLA projects. We have clinical researchers, most of whom are at CHLA. We have software architecture people like Andrew, who just got up here and talked, and who also know about data management. Machine learning people, that includes me, but it also includes a gentleman named Benjamin Marlin, who's not here today, who worked with me on the work I'm going to present. We have Christian Sheldon and his student Bushra and Eamon Keogh from Riverside, who we've sort of gotten our hooks into and are going to start working with us on some stuff. We've worked with a computational statistics person named Amy Braverman, and of course the wonderful people from Jeff Heer's group who do visualization stuff. And the amount of work that we've accomplished, I'd say, in the last 6 months by simply bringing these people on and farming our data out to them has been incredible. And I have a lot of confidence in that model. Now, there's pitfalls and challenges, especially communication stuff, that I'm going to revisit throughout this talk. But at the end of the day, I think there's value in facing those challenges. Rather than saying it's too hard to talk to people who are in a different field, I think it's better to open up the dialogue and figure out how to communicate, because you learn a lot from it, and you end up having a much more productive research approach. And going back to my father's quote, it's this idea that no matter how smart you are, how accomplished you are, how educated you think you are, there's always, any person you meet on the street knows something that you don't. And if you're willing to listen and be open, you may learn something from them. And I think we need to do that in research. We need to look to other fields, other disciplines, and we need to reflect that back onto what we're doing. Okay, so back to the A story. Analytical objectives of the project here at CHLA. Oh, and by the way, I apologize about the visibility of the slides. Paul V worked really, really hard on these. They look great. They look so professionally done. But because we're filming this, we have to have these bright lights shining on us, and it washes out the screen, so you can't see anything that's red. So apologize about that. Analytical objectives. So our main goals, and largely our vision is defined by my boss, Randall Wetzel, are let's see if we can discover physiologic patterns that have clinical relevance. And in particular, we'd really like to characterize physiologic patient similarity. These are very, very different tasks from a lot of the other research that's been described here and what is traditional clinical research, I think. I think a lot of traditional clinical research is focused on prediction, condition monitoring. That's, a lot of the stuff that Stuart Russell was describing. Monitoring the state of the patient and inferring about what's going on with them. All those kinds of things. Our task is not in opposition to that. We were presented with sort of this dichotomy of data-driven methods versus model-based methods, and Stuart had the bold line on his slide yesterday that said, we know a lot about the human body. We shouldn't throw it out. We should use that. And then we had other people get up and say, I don't care. I'm going to do it data-driven anyway. I don't think it really is either or. I think we should be trying all of these things. And it depends on what your analytical objective is. Our goal is we would like to try something that I call passive decision support. It's basically information retrieval. We want to retrieve similar patients from a database, but do it based on non-trivial notions of similarity, i.e., it's really easy to say, find me patients who are the same age as my guy. But it's not necessarily, maybe that will be helpful in some circumstances. But we would like to do something a little more sophisticated than that. Can we find patterns that characterize the patient's physiology, find other patients who have similar physiology, and then retrieve them and use them to sort of bring context to bear? As I said, this is very different. And largely, the goal of this is to help doctors navigate an ocean of information. That is really basically what it boils down to. It really is, I guess, an information retrieval task. Let's see. Yes, you can read that. It's basically cognitive scaffolding that's similar in principle to information retrieval tools that are ubiquitous throughout our lives. I mean, we use these things every day. Google, this is exactly what they're doing. There's I don't know if anyone even remembers what it was like to use the web before Google. I'm not even sure I knew how. I know I used it because I remember being on there, but I can't remember how I went about doing that. There's lots of data, and the data can be incredibly useful, and you don't necessarily need to take that data and compute a giant model and then put everything on the model. You can do sort of this data-driven approach where you, rather than use the model to do everything, you use the model to help you navigate the data but then ultimately you fall back to the data and you view the web page. And we do this, you see this with music recommendation. John's doing this with trying to get better ads on Yahoo. And so this is actually a common and familiar paradigm for people, and we're used to using these tools. And so we're interested in seeing if we can make decision support tools in medicine that use that same principle. And basically what that boils down to is similarity between patients. The other interesting thing about this, before I move on to clustering, is we can decouple the model from the actual tool. In other words, we should try to build tools that can be useful even when the model is maybe not accurate or has some flaws or problems. We don't want the tool to rise and fall with the model. This was the discussion earlier today about trust. What happens if the doctors reject the model? What if they're like, I don't trust what the little black box is telling me about the patient? Then they may not use it. And I think the answer to that I think Jeff sort of got at is, if you make the tool usable, regardless of what's going on with the model, people may very well find a way to use it. And you see this with Google, for example. If you tied Google to the model, what you would be doing is clicking the I'm feeling lucky button every time. Give me the top ranked result, and if that's no good, well, I'm screwed, and I'll just sort of brute force look through the web. But rather what Google does is try to just sift through the results and give you ranked results. But you're perfectly free to use controls on the side to filter them, to basically disregard what Google's telling you. You're perfectly free to skip over the first 10, 15, 20 pages and go down to the bottom because you think Google's doing a terrible job of understanding your query. And so we're thinking the same thing here. Rather than have our tool rise and fall with the model, make a tool that can be useful that allows the doctor to use it all the while disregarding the model. So, yeah. I mean, it sounds sort of ridiculous, but it's actually, and actually, I'm going to use this to highlight my point about multidisciplinary teams. This is an idea that was proposed to us by our collaborator, Benjamin Marlin. Ben is going to be a professor of computer science at Massachusetts Amherst. He knows nothing about medicine or medical informatics. He was interested in this project because his thesis was on machine learning with missing data, and I just emailed him and said, we have missing data problems, and he emailed me back and said, can I look at your data? I'd love to play with your data. And we said, sure, why not? And what's come out of this is a collaboration. And he's come out and visited a few times, and we started talking about this idea of decision support, and he was really worried about this notion. He said, look, especially early on, this idea of similar patient retrieval, we're probably going to suck at it. We're not going to be very good. And if a doctor uses it and starts looking around saying, I think these similar patients aren't very good, and they reject, and they're tied to that. They can't get around it. They're not allowed to say, I don't trust you, model. I'm going to do my own thing. Never mind the whatever black box similarity score you're using. I'm going to go and find people who are the same gender and the same age and all that. If you force them to use the model and they don't like the model, they won't use the tool. And Ben's background is in collaborative filtering. He worked on music recommendation at Yahoo, and he dealt with those same problems there. And when they were building their tool, they tried to apply the same principle of that. The tool needs to be flexible and not force you to use the model in the event that the model fails or you don't like the model. And he felt that would be even more important here where we're working with clinical experts. And I think he was right. And I think that those are the sorts of worries that we heard during our panel. So clustering. Here's a very dumb toy example. I actually think this audience probably doesn't need an explanation of clustering, but we'll go through it anyway. So here's a bunch of patients that are graphed based on two parameters, heart rate and blood pressure. Let's just pretend it's mean heart rate and mean blood pressure. It's not actually real data. So we run a clustering algorithm. We put them in groups. We draw circles around them. And then the next step would be, do these clusters mean anything? Well, in this case, I specifically designed the examples so they would and got labels from my clinical colleagues, so of course they do. Maybe the guys who have high heart rate and low blood pressure have shock. Maybe the guys who have high blood pressure and low heart rate have intracranial hypertension. This is just sort of a dumb toy example to give you an intuition of the sorts of things we're kind of interested in doing. I was going to prepare some slides about what the data's like, but fortunately Stuart Russell, Christian Shelton, Eamon Keogh, Suchi Saria all did my job for me, so I'm just going to throw this one slide up and just race through it. The data's high dimensional, it's multivariate time series. The data we're looking at in particular is sparsely and irregularly sampled. There's thousands of heterogeneous variables. The episodes vary in length. the data is incomplete, yada, yada, yada. The data is simultaneously problematic and difficult, and also fascinating for machine learning people. This is why people want to work with us. They're like, oh, I'll be able to get several years of NIPS papers out of this data set. And ultimately, that's what it's really about, right? So, our data is electronic healthcare records. What do people mean by electronic healthcare records? What they mean, whether they realize it or not, we've been talking about digital data here, but actually the digital data that people have been talking about here is, in large part, has been the high-frequency monitor data, which is not ubiquitously captured. It's captured at large research institutions that have money and resources to invest to get those systems. Your average sort of clinic or pediatric center or whatever, in their race to fulfill the government's mandates to get electronic healthcare records, most likely not getting those. They are getting the commercial or maybe even a homegrown electronic healthcare record system. What does this have in it? Most likely not the high-frequency monitor data. Most likely not the waveforms. So a lot of complaints were made about this data. People don't trust it. They think it's erroneous. They think it could be wrong. They think it's incomplete. Lots of people think that there's no way you could do legitimate science on this data. I have a suspicion they might be right, at least depending on the science you're talking about. If you're trying to understand the intricacies of the human body system, that's probably the data that you need, the high-frequency stuff. Nevertheless, lots and lots of places 5 years from now, there's going to be tons and tons of this data. As messy and irregularly sampled and sparse as it is, it's going to be there. And so we have two decisions. We can either write it off and say that it's not scientifically useful, and, well, we'll just have to wait till everyone can buy Bedmaster or some data system to capture all the high-frequency stuff, or we can see what we can get done with it. And that has sort of been the route we've elected to go, because we have a lot of it. We have about 20,000 episodes from over a couple of decades. This includes observations, so things like heart rate, but not at the high-frequency sampling rate. This is like on an hourly basis, maybe. There's labs, medications, interventions, diagnoses, all that stuff that everybody sort of expects would be in it. It's not the high-frequency monitor data. We actually do have that, and it's not that we're choosing not to use it. We are doing projects with that. We're very interested in it. We think that is valuable. It's just that we think we can also do interesting things with just the EHR data. So why? I sort of got into this. This stuff's going to be increasingly available and abundant. Randall would say that this is the data that doctors are making decisions based on. This actually represents an official clinical record of what happened. I'm sure there's people that would argue with that statement. I'm sure there's people that would say the doctors are seeing other data that isn't necessarily being recorded. That may very well be the case. But this is indeed the official clinical record. And then the third thing about why we might want to work with this data is what I said before, which is machine learning people think it's actually more interesting. With the high-frequency stuff, there's sort of a tendency to think that probably Stuart Russell's right. We probably should just build a giant model of the human body and run the data through that. With this more sparsely sampled physiological data, you can't do that. Those models won't work because those models depend on the data coming in much more frequently. Probably. Maybe I'm wrong about that. So an initial data set we constructed, we pulled out all the typical things, diagnoses, outcomes like length of stay, mortality, and then the physiological data, because that's what we're really interested in analyzing. We picked out 13 variables sort of to get a smattering of the different kinds. So you'll see that there are things that are sort of automatically captured, like heart rate. There are also things that are ordered as like lab tests, like pH, glucose. They're invasive. There's also clinical assessments that are sort of subjective assessments made by a clinician, so total Glasgow Coma Score. You will see that these are quite heterogeneous. Some of them are continuous. Some of them are basically categorical. Some of them are Gaussian distributed. Most of them are not. And they also vary widely in the frequency of measurement. And they not just vary across variables. You'll see variance in the sampling rate between patients. One guy may have heart rate measured every hour. Another guy may have it measured every half hour. You'll even see variation within a single patient. If the guy starts coding, they're probably going to record heart rate much more frequently than when he's completely stable and about to be discharged. So this is the data and just sort of an idea of the relative frequency of measurement. So what are we going to do with it? We want to do clustering of patients. Clustering usually requires you to have some kind of distance measurement to sort of say how similar two patients are. We have this data that's really heterogeneous, sparsely sampled. There's no sort of one-to-one matching that you can do. It's incredibly hard. We can do things like defining features manually. This is sort of the old-fashioned approach. I think machine learning people tend to find this quite dissatisfying. You feel like you're throwing out data. This is how the famous PRISM severity of illness score that Randall was involved in, that we actually still use today to stratify risk in pediatric intensive care unit patients. This is how this was developed. We could impute missing values. Indeed, the first attempt we made at clustering this data, this is what we did. We just said, let's pretend that if we don't have an observation of heart rate, it's the same as it was before. And you can do things like that. You can interpolate between nearest values. You know, these things can work fine. Eamon said that he thinks that there's no problem in doing this sort of stuff with time series data. Maybe when it's more sparsely sampled, like on an hourly basis, maybe he would worry a little bit more. We did that, and we got some decent results. By doing that, we were able to use simple clustering models like k-means to cluster episodes. But we found it deeply dissatisfying because we concluded that about 80% of the data we were clustering on was made up or imputed. That's not very satisfying, when you're clustering fantasy data. You can transform the data. Maybe since one of the big issues is the sort of variation in the sampling rates between episodes, maybe we'll bucket the data, and then we'll have a fixed dimensionality of our data. We still have variation in the lengths of episodes. We'll get to that. But let's say if we discretize time to an hourly basis, and then we bucket the data inside, maybe we take the mean value of all the measurements within that bucket. That's something you can do, and we actually ended up deciding to do this. Eamon left, but I was going to give him props and say that he coined the term for this called piecewise aggregate approximation. Also, fancier models. We can use Gaussian processes or something like that where we model the data as trajectories or functions. We can use continuous time Bayes nets. That's actually something I'm really excited about trying, and we're working with the Riverside people to do this. And I know Suchi has done some stuff with these kinds of models. So that's an option. For our first pass, we sort of did a combination between 3 and 4. We did transform and simplify the data to make it a little easier to enable us to use simpler models. But we didn't use just k-means clustering. We used maybe a slightly more sophisticated model, not tremendously. I want to point out that in doing that, the medical people that I worked with, and probably people in the audience, cry foul and say, you're making all kinds of assumptions that are invalid about the data. You're assuming it's Gaussian distributed. Oh my God, you're throwing out information, all that kind of stuff. When I did my education at Stanford, I did research for a while with Sebastian Thrun, the guy that built the self-driving cars. And his sort of approach to research, whenever people would come to him and say, I have a problem I want to solve, and I've drawn up this fancy model that I'd like to do. And he would just say, stop, stop, stop. Have you tried the simple thing yet? No, I thought I would do this thing. He'd be like, I don't want you doing anything complicated until you've proved to me that the simple thing doesn't work. And that's not the only approach to research, but that is that's sort of thinking like an engineer. And I think there can be some wisdom in that sometimes, that maybe we should demonstrate that simple things fail, and then when we understand why they fail, that gives us some insight into how to move on to a more complicated model. So, transforming the data. As I mentioned, we copped out and decided to simplify our problem a little bit. First of all, we truncated data to the first 24 hours. That gives us a fixed length of episodes, so we don't have to deal with the fact that some episodes are 12 hours and some episodes are 3 months, and that's really, really hard. But the doctors tell me that this is also clinically justified. They feel that, in general, in the pediatric intensive care unit, most of the action is happening in the first 24 hours, and that's where the patient's ultimate fate is really decided, probably. We also bucketed the data to 1 hour intervals. We discretized time, and we take the mean value. If there's multiple measurements within an hour, we take the mean value of those. This, of course, creates a new problem, missing data, because what if you have no measurements in an hour window? So now we have a new problem we have to deal with. We also unroll the data into a giant vector, so we are basically it's no longer a time series. We're sort of treating things as independent features in this vector. And I know that'll upset some people, but that's okay. So how do we deal with since we've turned our data into a fixed dimensionality, we can use simple clustering models now, but we have the missing data problem. So how do we deal with that? we elected to go with a mixture of diagonal covariance Gaussians. So it's actually a relatively simple model. There's one little, well, there are some other tricks that we put on it that I'll get into. So this is the cluster prior distribution. So that's the probability that your patient belongs in that cluster. This is the actual distribution over the data points given the cluster parameters. And we're assuming that the data points are independent and they're Gaussian distributed. A horrible abuse of variables like total Glasgow Coma score, and we decided we were okay with that for now. And finally, this exponent here is where we make the missing at random assumption. This is how we deal with missing data. We basically say that since the data is missing at random, we can essentially marginalize it out. We can basically ignore the missing data points. Also, a horrible abuse, clearly invalid. It's okay for now. Learning in this model is done using expectation maximization. This was described for learning with incomplete data by Gauramani and Jordan back like 15 years ago now, I guess. And this is sort of the standard workhorse in a lot of unsupervised machine learning. I did want to toss in, yes. Oh, yes, I'm sorry. R is what Ben terms the response indicator. It basically indicates did we observe a value for that variable or not. So if we're missing the value, it's 0, which means that the probability there goes to 1. So we're essentially that's how we're marginalizing out the missing data. If we observe the value, R has a value of 1, in which case the probability distribution there doesn't go to 1. One thing I want to toss in is we did put an informative prior on top of this data. So we did sort of an empirical Bayes method. I don't want to get too much into the weeds on that because, quite frankly, Ben understands that a lot better than I do. I'm still learning about that stuff. And if John asks me questions about it, I'll butcher it. So one of the big challenges with unsupervised learning and with our project is evaluation of clustering models. You know, we're putting the patients into groups. How do we know whether they're any good? We can do manual investigation, dive into the clusters, actually look at who's in there. Randall's always asking this. I want to know who's in there. And I think, you know, Randall, do you really want to look at 7,000 patients? But one of these days I'm going to take him up on that offer and just give him the spreadsheet. Descriptive statistics. We can plot things like how about cluster versus mortality and how is that distributed? Visualization. Jeff here comes to our rescue. We can tie clustering into a task with some sort of measurable success. Suchi sort of talked about this a little bit on the panel. And we do some experiments in prediction just to see if our clusters are useful for that. And then we can use clustering to do other useful things. So none of these is like a silver bullet. None of these gives us proof. Yes, our clusters are right. But with sort of a suite of these tools, we can get a sense of whether we're doing something reasonable and useful or not. So descriptive statistics on an actual clustering experiment we did. So this is, we ran the clustering with 20 clusters, so 20 mixture components. And this is the mortality probability in each cluster. In other words, what's the proportion of patients in each cluster who die? Oh, you know, that looks interesting. There's some clusters that are high. There's some that are low. For people who care about such things, we did a chi-squared test, and it turns out the null hypothesis that mortality is uniformly distributed is rejected. Great, wonderful. I don't know if that means much, but we did it to make the doctors happy. Some other descriptive statistics. What I've done here is I went to the diagnostic labels that we have, which weren't included in the clustering model. And I said, okay, let's pull out all the patients whose diagnoses fall into the respiratory category. And these are categories that are not from any standard ontology that I know of. They're from our specific database. And so these are just patients who had a respiratory diagnosis. And then this is their distribution across clusters. And so there's something kind of interesting here. There's one cluster that seems to be really high. And those are raw counts, not proportions. Yes. I don't want to say anything stronger about it than it looks interesting, because I'm not convinced that there is much more to say about it than that. Here's another diagnostic category, neurologic. So this is, of course I'm showing you the interesting ones. There's ones where it's much more flat, and obviously I wouldn't put those in the talk. Visualization. These are some little graphs that we made. Ben termed them the physiome. So what you're seeing here, the red, which you probably cannot really make out, there's a dark red line in the middle of the red, and that is the mean value of that parameter over 24 hours for the entire patient population. And then the shaded red region is like one standard deviation above and below, I think. The blue is for this particular cluster. Same thing, mean standard deviation. So, this is kind of an interesting looking group. The doctors would point out to me that when I show this to some doctors, they say, I don't know what this is. I show them to Randall, and he says, I know exactly what's going on with this cluster. So this is one of the challenges inherent in this kind of unsupervised learning. And of course, this is a challenge in these multidisciplinary collaborations. I have to sometimes convince them we're doing the right thing, and other times temper their enthusiasm about some results we got that I'm very suspicious of or worried about. So we see high blood pressure, brisk cap refill, high SpO2, normal glucose. Hey, it's a low mortality cluster. They look healthy. Great. Another visualization. Low blood pressure, prolonged cap refill, high heart rate, high respiratory rate, low pulse oximetry, low pH. I showed this to the doctors, and they say maybe it's shock, and it's actually it's also a high mortality cluster. So that's kind of interesting. Again, nothing. It's not proof. Doesn't constitute proof. It's not definitive, but it is interesting, suggestive, let's say. So I mentioned that another way to evaluate these clusters is to tie them to some predictive task where we have an actual measurable success. So what we decided to do is predict mortality, because that's what you do in the PICU. And also we could try to predict diagnosis, but Dr. Wetzel believes that the diagnostic categories are human gibberish, so we ignore those for now. I want to point out, and actually I think for this crowd this isn't that important, but for medical crowds we have to be careful and let them know we're not trying to build a good mortality predictor here. This is not the optimal way to build a mortality predictor. The much better way would be to just dispense with the clustering, and just actually try to optimize a classifier. That's not what we're trying to do. We're just trying to see if using the clusters to do something that tells us that the clusters might have some information in them. The basic idea for what we do here, how we use the clusters in classification, is we train a separate predictor for each cluster. And then when we make predictions, we basically do, we sort of average the cluster predictions for each guy. We average across the cluster predictions, and it's weighted by that test example's membership in those clusters. So it's basically a weighted mixture of predictions. And then we compare it to a non-cluster model. This is similar to, but it's not a mixture of experts, because if we were doing a mixture of experts, we would have done the clustering and the classification training at the same time. We would have optimized the clustering for the actual prediction. So that's not what we're doing here. We chose two models. There are other ones we could have picked, and Suchi suggested that one that we should try that she was right about that I'll mention later. One is a weighted Bernoulli model. Basically, each cluster has a mortality probability, and that is what we use to make a prediction about patients who belong in that cluster. If more than half of those patients died, then we say patients in that cluster will die, and likewise the other direction. And so the one sort of catch here is it's actually a weighted, when we compute that parameter, it's weighted by that person. The person's contribution is weighted by their membership in the cluster. And just to point out, the non-cluster Bernoulli model would just be the overall population mortality rate, which is 6%. So our non-cluster Bernoulli model thinks everyone should live, which is maybe wishful thinking, but clearly not true, and obviously this is a bad model. The other thing we did is a weighted logistic model. We had to do some feature selection here. We couldn't use the raw data vectors. So we chose the max and min values for each variable within the 24-hour time window. And then we also threw in patient age just for good measure. And so we just do, basic logistic, linear logistic regression. Bye, John and Alina. Thank you for coming.
You're safe.
Yes.
John now.
Yes. I managed to delay. Okay, I'm good. Yes, I know.
Okay.
So we had to, one thing we have to point out is that we use the clustering model to impute missing values before we do the feature extraction. We're not making them up, we're getting them out of the model, which is making them up, but maybe in a slightly more principled fashion. The other thing I want to point out is we use regularization here. Suchi mentioned regularization in her talk. The idea here is that some of the clusters we're training on may have 5 patients in them, in which case we could get really crazy weights on our predictor and really unreasonable likelihoods. So we want to keep the weights small, especially when we don't have a lot of data in a cluster. And then the contributions to each training example within the cluster when we're training are weighted by their membership. And then when we make predictions at test time, we do a weighted average between all the predictions. So here are some results. This is area under the curve, because this is what the medical people like to see. We have 8 different models here. The B and the L are the baseline models, the dumb Bernoulli model and the logistic regression without the clusters. And then the C models, the 5, 10, 20, are 5, 10, and 20 cluster models. And there's the Bernoulli and the logistic. So there's 2 interesting things to point out here. The best model is indeed a cluster model, not tremendously so, probably not statistically significant, but it does do a little bit better than the logistic regression. And it's worth noting that the performance actually goes down with the number of clusters, because what we're getting then is we're getting some clusters that are really, really small and probably are bad at predicting. I think the more interesting thing is the fact that the Bernoulli model based on clusters actually starts to approach the performance of the logistic regression. And this is the dumb Bernoulli model, where we just think that people live or die based on which cluster they're in. And this seems to suggest that maybe as the number of clusters go up, we're actually capturing some kind of information about mortality. Yes, sir?
It's the nearest neighbor accuracy. As the clusters goes to infinity,
yes.
it's the nearest neighbor. So it's the nearest neighbor accuracy.
No, I don't. This is what Suchi dinged me on. Yes. So, but no, it's good. I'm glad we got that into the talk too, and I'm glad you were able to pick up for John. I should have known that I wouldn't get things past you too, Christian. I should have known. So, no, I'm just kidding. We also, because we had to worry about class imbalance, because only 6% of our patients died, we decided to try some other evaluation metrics. I'm only going to share one, Matthews correlation coefficient. I actually talked to John this afternoon. He said 6% is probably high enough that we didn't have to worry about those things. He said area under curve starts being susceptible to class imbalance when you start getting down to really, really small numbers. So, but Matthews correlation coefficient is basically we're measuring the correlation between our predictions and the actual values. And it's interesting, it goes up. I mean, this is part of the challenge that we have to, when we're evaluating these models, we have to find the right evaluation. And even the literature isn't fully in agreement. And, we heard this in the discussion about cross-validation, that this is a thorny issue. So next steps. We want to increase the scope of our data. We want to add more physiologic variables. We're obviously very worried about interventions. It's when we look at some of these physiome graphs, what we see is this patient appears to be stabilizing. They must have gotten medication. Also, age. We're not taking age into account. When we cluster people on physiology that is dependent on age, we may very well be putting sick teenagers in with healthy infants. So that's something to consider. But what we'll find out is if we have a properly designed tool, we can account for that. We're going to improve our evaluation toolkit. So Suchi suggested nearest neighbor classification, and now Christian has too. And that's an excellent point. We should do that. And find other metrics for measuring the quality of the clusters, maybe. We want to relax our modeling assumptions. Ben and I both feel, this work was done with Ben Marlin, we both feel that we need to get rid of the bucketing and we need to get back to the data itself and be as close to the data as we can. So maybe we'll try some fancier models, CTBNs, Gaussian processes, other things. We also need to address the unalignment, the fact that patients come in at different points in their time courses. And then build a similarity tool. So very quickly, similarity tool, which you're about to hear more about. This is a 5,000 by 5,000 matrix of patients, and each entry indicates the similarity of that patient to another patient. The way we developed this is we ran 20 different clustering runs and then sort of aggregated, essentially measured how frequently patients end up in the same cluster together. White is extremely similar. Black is very, very different. They were never in the same cluster. So if I resort them by mortality, so let's see how well you can see it. I'll help you. The thin bands are the patients who died. The thick parts are the patients who lived. So it's not perfect, but you kind of see more black in the thin bands along the side, and you see more white in the upper left-hand corner and the lower right-hand corner. Patients who died are more similar to patients who died. Patients who lived are more similar to patients who lived. So that looks kind of nice, and hopefully it can be useful. What can we do with it? So these are similarity scores. We can use them to generate a ranked list of patients who are most similar to the one you are treating. And we can use this to help clinicians navigate the ocean of data. And if we have a good tool, then maybe they can do something useful with that. So that is the next part of our presentation.
Which I think we better move right on to.
Yes.